Okay, so this is the idea of all of chapter 13, is that we're going to find antiderivatives, and the name is pretty self-explanatory. Antiderivatives just have the inverse relationship to the derivative. So if we have some function lowercase f, and I tell you that is the derivative of the function capital F, well then we would also say that capital F is the antiderivative of lowercase f. So my first example says, we know 2x is the derivative of x squared. That means that x squared is the antiderivative of 2x. So it's just the converse of the derivative here. The notation that we're going to use when we talk about antiderivatives looks like this tall little squiggle. And it takes some practice to write these pretty well. But I mean, that's what you do, is you have a little hook on top and then a little hook on the bottom. And sometimes this is called like the integral sign. Sometimes it's called the antiderivative sign. But antiderivative and integral, those words are mostly synonyms. So if I ask you for the integral of 2x or the antiderivative of 2x, it's the same thing. So whenever you see this tall little squiggly symbol, the way you would read it out loud is by reading the antiderivative of, and whenever you see the little dx at the end here, it's like the other bookend. It's just telling you, like, we're taking the antiderivative of the stuff that lies in between the tall squiggle and the dx at the end. And so you would say with respect to x whenever you see dx. So reading this out loud, you would say the antiderivative of 2x with respect to x is equal to x squared plus c. That's how you read this little box out loud whenever you see it on paper. And again, what happens between the tall squiggle and the dx, that's what we're trying to take the antiderivative of. And if you were being really formal, then this stuff in here is what you call the integrand. And so, like here, my integrand is 2x. Okay. Now, you'll also notice that this says the antiderivative is x squared plus c. That lowercase c stands for any constant. So it could be 5, it could be 42, it could be -7. And it's actually always true regardless of what number you choose for c, right? I could tell you that the antiderivative of 2x is x squared plus 7, or I could tell you that the antiderivative of 2x is x squared minus 42. And those are all true statements, because if I take x squared plus 7, and I do the derivative with respect to x, well, that derivative is 2x, right? The 7 goes away. And if I told you that that antiderivative was x squared minus 42, and I take the derivative with respect to x and I check, well, the derivative is still 2x because the minus 42 is a constant that goes away in the derivative. So whenever you take an antiderivative, we're always going to write a plus c on the end, because we're adding some constant where you are free to choose what that constant is, and you still get the same derivative when you take the derivative of your antiderivative. Right? You'd still get back 2x. That can be a little bit tricky, because the derivative isn't like that. You don't take a derivative and add plus c, but whenever you take an antiderivative, you're always going to add the plus c. Yeah. Okay. So let me give like just one more example before we move on. Like if I ask you for the antiderivative of 4x cubed with respect to x. Again, this is read the antiderivative of 4x cubed with respect to x. And what would be this antiderivative of 4x cubed? It would be what?
4x squared.
So that would be taking the derivative. If I had 4x cubed and I wanted to take the derivative with respect to x of 4x cubed, then the power rule would say bring down the 3. 4 times 3 is 12, and then you subtract 1 from the exponent. And so that would be the derivative.
So then if you
But in this case,
you just put the 4 back up for the exponent?
X to the fourth.
it's going to have an x to the fourth, yeah. And then what happens to the 4 out in front?
U goes away.
Yeah. Yeah, perfect, Clarissa. The 4 just goes away because just checking our work here, if I take the derivative of x to the 4th, that would be putting the 4 out in front and then making the 4 into a 3. And so that derivative is equal to my integrand, and so it checks out. This is the correct antiderivative.
So you do the opposite.
I-
So you add on the top,
You add 1 on the top,
and then you put the.
and then, yeah, you divide the whole thing by your new exponent. Yeah, it's the reverse power rule.
Oh, okay.
It's exactly the opposite
I
of
was
what we've
like-
been doing for the derivative
I was
power
confused.
rule.
I was like,
I'm also going to add this plus c, because if this were x to the 4th plus 5, then I would still get a derivative of 4x cubed. If it were x to the 4th plus 300 trillion, then derivative of 300 trillion is still a constant. So this c can be whatever number you want it to be. So the antiderivative is x to the 4th plus c.
That's over 300 trillion x cubed. Like, then you have to do some serious math to find that.
Yeah, then you would have to keep your constant. Okay, so now moving on. On the next page, I have a box, and anytime I put something in a box on your lecture notes, that means I need you to memorize it. So I need you to memorize these 5 things, and these should be labeled 1, 2, 3, 4, 5. I don't know why it's not labeled here. So the first thing is the antiderivative power rule. And like Deanna said, this is just the reverse of what you did for the derivative power rule. So whenever you see x to the power n, you're actually going to divide by, and this is a typo, it should be n plus 1. In your lecture notes, is that n plus 1 on the denominator? Is that actually correct there? Seriously?
On the denominator?
This has been happening to me a lot lately where I know for certain, I know I've made this correction, and then it appears wrong. Okay, so let me show you what correction you need to make, because it's actually really, really, really important. So
just erase the whole thing.
we are going to have the antiderivative of x to the power n equal to 1 divided by n plus 1 in the denominator there. Then times x to the power n plus 1 plus c. So this corresponds to raising your exponent by 1, or adding 1 to the exponent, and then dividing by your new exponent. Now dividing by whatever your new exponent is. So like in my example, I gave the antiderivative of x squared. You add 1 to the 2 in the exponent, and that becomes x cubed, and then you divide the whole thing by your new exponent. So you divide by 3. And so my antiderivative is going to be 1/3 x cubed plus c. And the good thing about antiderivatives, the good thing is that you can always check your work really easily. If you found an antiderivative and you're just not sure about it, just go ahead and take the derivative of your answer, and it should be equal to what you started with. It should be equal to your integrand. And so if you don't trust this example, you could say, well, what's the derivative of 1/3 x cubed? And the derivative would be bringing down the 3. 3 times 1/3 is 1. And then you subtract 1 from the exponent and you get 1x squared. And that's equal to your integrand. That's answer is equal to what you started with. So that's a way to check your work here. Okay, but again, make sure that you make this correction, because that's going to be very, very important. The second thing is the antiderivative of an exponential function. And so here I have the antiderivative of e to the power kx with respect to x. You're going to keep the e to the power kx part, and where it has that k in the exponent, that k is just any constant you want it to be. So in my example, I have e to the power 5 times x. That antiderivative is going to be 1/5 times e to the power 5 times x plus c. And so you'll check to make sure if I let k be equal to 1, then that would just be the antiderivative of e to the power x. And the antiderivative of e to the power x would be 1/1 times e to the power 1x. And so that would be your antiderivative if you just have e to the x by itself. And check to make sure that makes sense, right? The derivative of e to the x is e to the x. And if we start from here, 1/5 e to the power 5x, and I take the derivative, that would give me, chain rule says 1/5. The derivative of e to the x would keep the e to the 5x. And then again, chain rule is telling me multiply times the derivative of that inside function, where my inside function is 5 times x. So the derivative of 5 times x is 5. So the 1/5 times 5 is going to cancel, and that just gives me e to the 5x. And that checks out, doesn't it? Because the derivative of my antiderivative is the thing I was trying to take the antiderivative of in the first place. So again, that's a good way to check your answer. Number 3 is the antiderivative of the reciprocal function. So 1/x is what I call the reciprocal function. And this is going to be the natural log of absolute value x. And remember that 1/x is equal to x to the power -1. And so that means if you're taking the antiderivative of x to the -1 power, that's also the same thing. It's natural log of absolute value x plus c. And you might remember this if you memorized your derivative table. You know that the derivative of the natural log function was 1/x. That was something we had to memorize in previous midterm exams. So that should check out that this antiderivative, when I take the derivative, it returns the 1/x. I want to compare two things. I want to compare my antiderivative power rule from number 1 with this in number 3. Because my antiderivative power rule, if I followed this for x to the -1 power, it would give me -1 plus 1 is x to the 0 power. And then I would have to divide by my new exponent, so I'd divide by 0. But x to the 0 power is just 1, so this is just 1/0. But this is not defined, right? You can't divide by 0. So that's why we say that the antiderivative power rule doesn't work when the exponent is -1. And that's why we have to resort to this definition whenever x is to the power -1. So that's special because the -1 power is the only integer power where when you take the antiderivative, you don't get x to another integer power. You actually get a natural log function, which is weird. But the last two, while you do have to memorize these and be familiar with them, they should sort of feel like common sense. And the derivative had the same two properties. We talked about how the derivative had the properties of additivity and homogeneity. Well, the antiderivative has the same thing. It just means if you're taking the antiderivative of two functions, like the antiderivative of the sum f of x plus g of x, where those are any two functions, that's the same as taking the sum of the antiderivative of each function. So the first line says the antiderivative of f of x plus g of x with respect to x is equal to the antiderivative of just f of x with respect to x plus the antiderivative of just g of x with respect to x. And so if I let my f function be x cubed and my g function be negative e to the 3x, all I have to do to take this antiderivative is just take the antiderivatives of x cubed and negative e to the 3x separately, and then add a plus c on the end. And then the last thing, the derivative homogeneity rule, says that if you're multiplying by some constant factor, like some k inside the antiderivative, you can just take it outside of the antiderivative and then otherwise take the normal antiderivative. So like, if I see the antiderivative of 5 divided by x, I notice that that 5 over x is just 5 times 1 over x. And recognizing that, I can pull the 5 outside of my antiderivative out front. Just take the antiderivative of 1 over x, which is natural log absolute value x, and then keep the times 5. But we did the same thing with derivatives. So that's not brand new or anything. Any questions about these 5 rules? Yeah, like I said, in the box, those are the 5 rules we're going to have to memorize about antiderivatives. And make sure we have this correction in your notes, because the antiderivative power rule, we're going to use that more often than we use any other antiderivative rule. Just kind of like the derivative power rule we used over and over and over again so far. So on the next page in your notes, we've got a bunch of examples. And I'll let you guys tell me what all these answers are. The first one says, what's the antiderivative of 6x with respect to x? What's my antiderivative? So look back on the previous page and look at your rule number 1. It's the antiderivative power rule. And it's telling you in the rule just the general form. Like if you're taking the antiderivative of x to the power n, in our case, what is that n power? I have x to what power here? 1, yeah. So when I use that antiderivative power rule, n is 1. Also, because of my rule number 5, the homogeneity rule, when I see the 6 out in front, I can just pull that outside of my antiderivative. So I can rewrite this as 6 times the antiderivative of x to the 1 power with respect to x. And this is going to be 6 times, what is just the antiderivative of x to the 1 power? That would be the derivative. Again, look at rule number 1 on the previous page.
Would it be 1 over n minus 1 plus 1?
Okay, so I'm just going to write the rule over here on the right side of the page.
1 over 0.
Over here, I'm going to write that the antiderivative of x to the n power, for any n, it says it's supposed to be equal to 1 over n plus 1 times x to the power n plus 1.
All 1.
So if my n is equal to 1, then that means that my antiderivative is going to be 1 divided by 1 plus 1, so 1 over 2, times x to the power 1 plus 1, so x to the power 2. So yeah, if you remember the derivative power rule really well, just think I have to move exactly in reverse. I have to add plus 1 to the exponent instead of subtracting 1. And then I have to now divide by my new exponent. I don't want to confuse you, but for the derivative power rule that we've already learned, you subtracted 1 from the exponent and you multiplied the whole thing times your old exponent. With the antiderivative power rule, you add 1 to the exponent and you divide everything by your new exponent. So this is going to be 6 times 1/2 x squared, which we could say final answer after I simplify, this is going to be 6 times 1/2. This is 3x squared. Okay.
Oh, okay. Because I thought, why did you have this? But it was, you just multiplied it from, yeah, sorry.
Yeah, I had to use rule number 5 to bring the 6 outside of the antiderivative. I used rule number 1 to handle the power rule part. Okay, so let's talk about this next one. So what is the antiderivative of 18r squared with respect to r?
You do the same thing, leave the 18 out.
Uh-huh. I should bring the 18 out because that's just a constant multiplier. So I have 18 times antiderivative of r squared with respect to r. So this is going to be 18 times what?
Right? 1/3. 1/2. 1/3.
I hear 1/2, I hear 1/3.
1/3 R 3 R.
Yep.
Sorry. Oh yeah.
This is going to be 1/3 r cube. And by the way, I forgot something really important in my first example.
Plus C.
Thank you, Zoe. I forgot plus c. Yeah, I never forget plus c.
And like in theory, just be
Why is it 1/3 and not 1/2?
Because we're going to add 1 to the exponent, and then we're going to divide by our new exponent.
2 plus 1 on the bottom.
Yeah. Remember that correction I made? And I was like, oh, this correction is so important. It should be 1 over n plus 1
So 2 plus
times x to the power n plus 1.
Oh.
Yeah, so
Oh.
that was super important because this was wrong, what I had written down there before. That was bad. The n plus 1 is critical, very important. Okay, so 18 times 1/3 is going to be 6. And so 6r cubed plus c, that will be my final answer for that example. Over here, I have the antiderivative of 16 t cubed with respect to t. What is the antiderivative of 16t cubed with respect to t?
6t times 1/4 times t to the 4th.
Perfect. Very good. The 16 stays the same. Times 1/4 times t to the 4th. Because you added 1 to the exponent, and then you divided by your new exponent. And we can't forget the plus c. Thank you. So 16 times 1/4 is 4. So this is going to be 4t to the 4th plus c as our final answer. The next example says, what is 36 times x to the 5th? Or I guess I should say, what is the antiderivative of 36x to the 5th with respect to x?
Times 1/6 x to the 6th.
Yes,
Plus
perfect.
c.
The 36 comes out of the antiderivative and stays the same. I do x to the 6 because I add 1 to the exponent, and then I divide by 6 because I divide by my new exponent, and then I don't forget the plus c. What is 36 times 1/6?
6.
Yep. So then my final answer is 6 x to the 6th plus c. Okay, what is the antiderivative of 2022 with respect to x?
2, it's undefined, right?
It's a trick question.
It's undefined, I think.
It's a constant. No, wait. It is fine.
Oh, yeah.
Remember, when you're taking an antiderivative, you're always thinking, what function is there where if I took the derivative, it would give me 2022?
X.
1 x to the
Yeah.
yes.
Having
X to the
one
negative 2021. X to the negative x to the half.
No. If you had 2x squared plus 2022x, then or like the derivative of 2022x will leave you with 2022.
Okay, Cyrus is right. The derivative of 2022x would just leave you with 2022, right? So this is saying 2022x plus c is going to be my antiderivative. And think about that. Whenever I take the derivative of 2022x, that just gives you 2022. So that's the correct antiderivative. Also, if we just remember that x to the 0 power is equal to 1, multiplying by 1 doesn't change anything. Like I could have 2022 times 1, and that still gives me 2022. We could say that this 2022 here is the same thing as 2022 times x to the 0 power. So if I take the antiderivative of this with respect to x, the 2022 stays the same. Nothing happens to it. And then if I use the power rule on x to the 0 power, I add 1 to the exponent, so 0 plus 1 is 1. I get x to the 1 power, and then I multiply times 1 divided by my new exponent, which is 1 over 1. So then I would get 2022 times 1 times x to the first power. That's just 2022x, which goes along with your intuition that Cyrus figured out for us in the first place, which is I just know that 2022x, when I take the derivative, gives me 2022. So then working in the opposite direction tells me that this antiderivative of 2022 with respect to x must be 2022x plus c. Okay, let's go with orange here. What's the antiderivative of 7z minus 1 with respect to z?
Is it the additivity rule? The additivity
Yeah.
rule?
Yeah. So my additivity rule
7 minus
would say that this is the same thing as the antiderivative of 7z with respect to z minus the antiderivative of 1 with respect to z. We just have to take each of those antiderivatives.
7 minus
So the next question you need to answer, we'll just do this first one. What is the antiderivative of 7z with respect to z?
because you said x.
Yeah. So this would be a power rule thing because z is the same thing as z to the 1 power. And so when we do the antiderivative power rule, we add 1 to the exponent, and that becomes z to the 2 power. And then I have to divide by my new exponent, and so I have 7 divided by 2 z squared. Now what's the antiderivative of 1 with respect to z?
1x squared. No, 1x.
You were doing good until you said squared. And our variable this time is z. So the antiderivative of 1 with respect to z is just going to be 1z. And then I can't forget plus c. And you can double check your work. We could take the derivative of 7/2 z squared minus z plus any constant you want and verify that that derivative should be 7z minus 1. Okay. Back over here on the left, I'm looking for the antiderivative of 5y cubed plus y squared minus 10y minus 6. So rule number 4, I think, the additivity rule, just tells you that you can take the antiderivative of each of those terms separately. Just individually take the antiderivative of 5y cubed, then y squared, then negative 10y, then negative 6. So what's starting off just the antiderivative of 5y cubed? Perfect. Add 1 to the exponent to get 4, and then divide by your new exponent. Okay, same thing for y squared. Add 1 to the exponent to get y cubed, and then we divide by the new exponent, so we get 1/3. Same thing for 10y. We add 1 to the exponent to get y squared, and we divide by 2. 10 divided by 2 is 5. And then lastly, with the negative 6, that would be like negative 6 times x to the 0 power. So then taking the antiderivative is just going to be negative 6y plus c. Sorry, I'm going to rush you a little bit because I want to get through these notes today. On Thursday we have even more planned, so I can't spend more than one day on this stuff. The next one says antiderivative of square root x. And you may remember, you should remember, that square root x is the same thing as writing x to what power?
-1. No, 2.
1/2.
1/2.
That's okay. E for effort. The antiderivative then of square root x is the same thing as the antiderivative of x to the 1/2 power. And now that we have x to some power, I can use my power rule, which tells me add 1 to the exponent. And adding 1 to the exponent is going to give me 3/2 in the exponent. And then I want to divide by 3/2. But dividing by 3/2 is the same thing as multiplying by, thank you, by the reciprocal. It's the same thing as multiplying by 2/3. So my answer is going to be 2/3 x to the power 3/2 plus c. Again, this is just using the power rule. Over here on the left, I have antiderivative of 1 minus square root t with respect to t. And so remember, if you have two different terms, our additivity rule says worry about them separately. Antiderivative of 1 with respect to t is going to be t. then square root t is like t to the half power. So this is going to be like minus the same thing as the antiderivative of x to the half power, but now with t's. 2/3 t to the power 3/2 plus c. Remember, add 1 to the exponent, divide by your new exponent. Over here we have 26 divided by x cubed, but you might remember that 1 over x cubed is the same thing as just x to the power what?
-3.
Thank you, Clarissa. That is -3. The -3 power means you can put it in the denominator and make the power a positive number, right? So this is the same. I can also bring out this 26, because that's just a 26 multiplying everything. So I might bring that out in front of the antiderivative, and so I write 26 antiderivative of x to the -3 power with respect to x. So this is going to be 26 times. My antiderivative power rule says I take that -3 exponent and I add 1. So -3 plus 1 is,
Whatever
it's -2. And then I have to divide by my new exponent, which means I multiply by -1/2. So simplifying, taking half of 26, well, half of 26 is 13. I have a negative in there, so it's going to be a -13 x to the -2 power. Or if you want to, you can write it as -13 divided by x squared, because the -2 power means that you can move the x squared into the denominator and make it positive.
Plus C.
Ah, you got me, plus c. Okay. I know it's hard to remember the plus c. I used to have a calculus teacher that would take off points if you forgot to write plus c. I'm not going to do that to you, but I will tell you that there are going to be questions where if you forget the plus c, it's going to screw you up as you go on to solve the rest of the problem. So like remembering it is going to be actually necessary for some problems you'll see on the exam. Again, I'm trying to move rapidly through these things, so I'm not going to work all of them, but we haven't done one with an exponent yet. So let's look at this one below it that says antiderivative of 7e to the 5x. If I bring the 7 out, this becomes 7 times antiderivative of e to the 5x. And everybody look at your sheet of rules that you're going to go home and memorize today. And the sheet of rules we're going to go home and memorize. Number 2 says that the antiderivative of e to the 5x is 1 divided by 5 e to the 5x plus c. So this is going to be 7 times 1 divided by 5 e to the 5x plus c, or you could write it as 7/5 e to the 5x plus c. You might be wondering, how do I tackle this next one? Well, I can actually divide both of these terms by the t, and that's going to be the correct way to do it. There's no, by the way, with antiderivatives, there's not a product rule for antiderivatives, there's not a quotient rule for antiderivatives, and there's not a chain rule for antiderivatives. You can't rely on those the way we used to for derivatives. So here, there's not going to be a quotient rule we can use. Instead, I'm just going to say that t squared divided by t is t, and then I'm going to add 1 divided by t, which is just 1 over t. But also, we need to remember that 1 over t is the same thing as t to the negative 1 power. So this is going to be like antiderivative of t with respect to t plus antiderivative of t to the negative 1 power with respect to t. And you can do your regular power rule on both of these. So this is going to be 1/2 t squared for the first one. Then the antiderivative of t to the negative 1 power is what? It's weird. The antiderivative of t to the negative 1 power would be natural log of absolute value t. So back here I write natural log of absolute value t plus c. Okay, so then I'm going to move on to this next example 1, where we're going to be applying antiderivatives to real-life scenarios. And the trick here for these word problems is we have to remember that the derivative is a rate of change, and the antiderivative is something that undoes a derivative. So if I tell you a certain formula to find a rate of change, if you take the antiderivative of that formula, it now no longer tells you about the rate of change, but it tells you about that property itself. So, for example, this tells me that the velocity of a runner in miles per hour during a 3-mile race is going to be a function of time, where t is in hours. Okay? This says, remember that velocity is the first derivative of distance with respect to time. So we're saying velocity is equal to the derivative of distance, I'll use lowercase s to represent distance, with respect to time. So here, this equation becomes ds dt. The rate of change of distance over time is equal to 9 minus 6 t. Now, what I'm going to do now is take the antiderivative of both sides with respect to that independent variable t. I'm going to say on the left side, I want to take the antiderivative of the derivative of distance with respect to time with respect to time. And on the right side, I'm going to say I want to take the antiderivative of 9 minus 6t with respect to time. So I'm keeping my equation balanced because I'm doing the same operation to both sides. On the left side and the right side of the equation, I've taken the antiderivative with respect to time. On the left side of the equation, these dt's are going to cancel out because I've got a dt in the numerator and a dt in the denominator. So dt divided by dt is just 1 multiplying by 1 goes away. So on the left side, I get left with the antiderivative of 1 with respect to s. If it's just blank, that's the same thing as the antiderivative of 1. You can think of dt divided by dt as 1 if you want to. And then on the right side, I get, well, I can use the rules that we know and say that this is going to be antiderivative of 9 is going to be 9t. And then this t with the negative 6t is going to become a t squared because I add 1 to the exponent. And then I divide by my new exponent, so 6 divided by 2 is 3. And I can't forget my constant. So then this tells me that the antiderivative of 1 with respect to s is just going to be s. And so just like I promised, the antiderivative undoes a rate of change. They originally gave us a formula in terms of the rate of change of distance over time. Basically, they gave us a formula for velocity. We took the antiderivative with respect to time, and it undid the rate of change. So now, what we're left with is a derivative, what we're left with is a formula for just distance. Not the change of distance over time, but just distance. Now our question here says determine the value of time when the runner finishes the race. And we're told that this is a 3-mile race. And so we're asking, what is t when my distance is equal to 3 miles? And so I can use my formula down here. And setting my distance equal to 3 miles, this says that 3 is equal to 9t minus 3t squared plus c. And if I really want to solve this for t, I need to figure out what is that c value. And to solve for c, I need to determine, well, I'll show you, hold on. Solve for c. I do know this, that my distance is going to be 0 whenever my time is 0, right? At the start of the race, both the time on the clock is 0 and the distance you've traveled is 0. And so if I plug in s equals 0 and t is equal to 0 into this formula right here, s0 equals 9 times 0 minus 3 times 0 squared plus c. Well, this is 0 equals c, so that tells me what my value of c should be. In this case, c is 0. But that's not always going to be the case. We're going to find some other word problems where c is not equal to 0 and it actually has a role to play. Okay, so knowing that c is 0, I can come back here and write that 3 is equal to 9t minus 3t squared plus 0. And that means that I have this quadratic equation if I just rearrange it a little bit. I'll add 3t squared to both sides. I'll subtract 9t from both sides. And I also should divide everything by 3, so I get t squared minus 3t plus 1 equals 0. And so that tells me the times t that solve this quadratic equation are going to be such that that factors as t. What multiplies to give 1 and adds to give negative 3? Like nothing. So let's use the quadratic formula then. Quadratic formula always works. So we have negative b, negative 3 is 3 over 2 times a, 2 times 1 is 2, plus or minus the square root of b squared minus 4ac, so that's 9 minus 4 over 2 times a. So my values of time are going to be an hour and a half plus square root 5 over 2 and an hour and a half minus square root 5 over 2. Square root 5 is a little bit larger than square root 4, so it's a little bit larger than 2. Divided by 2 means it's just a little bit larger than 1, and so one of these is going to be correct and the other one will be incorrect. And I think this lower one is the value that actually matters for us. Because an hour and a half is a long time to run 3 miles. Like a typical 3-mile time is like 25 minutes or 30 minutes or something like that. 20 if you're fast. So this 3 divided by 2, that's 1.5. That's an hour and a half. I think it's going to be less than that, so I'm going to choose the value of t that is 3/2 minus square root 5 over 2. Okay. So that's going to be the value of t when the runner finishes the race. If you had a calculator on your exam, you could do 1.5 minus square root 5 over 2. You can find out what that is. But it should be like 1/3 of an hour, around there. Okay, we've got 8 minutes. I'm just going to skip to a problem that has something interesting. Like this one. On example 5, it says, on January 1st, 2020, the population of Midland, Texas was 140,000. For the next 20 years, some economist projects the growth rate. So they make a model that just represents an approximation. The projected growth rate is going to be about, let's say, 30,000 divided by t. And this t variable represents the number of years after January 2000. So if we make a little table of year and the t value, if the year is 2000, the t value is 0. If the year is 2010, the t value would be 10. If the year were 2020, the t value would be 20. If it were 2030, the t value would be 30, and so on. So hopefully that's clear what we mean by the t variable. So let's find the function f of t that gives the projected population. That should be projected. In year number t. So the year would be like 2000 plus t, right? The way that we've figured that t variable is going to work. It's the number of years after 2000. Okay, so trying to find this function, capital F of t, and it's asking for a function that describes the population, whereas this represents the growth rate in people per year. In other words, a growth rate in people per year, that's a rate of change of the population. And a rate of change of population over time would be like dp dt. Right, so I'm saying the derivative of population with respect to time would be 30,000 divided by t. Remember, dp dt is talking about the rate of change of the population with respect to time. So let me write that again. I'll just rewrite dp dt is equal to 30,000 over t. And now I want to take the antiderivative, because I know that antiderivatives undo a rate of change. And I don't want this formula for the rate of change anymore. I want the formula for the population. That's what my question asks, is I want a function that gives the population, or the projected population. So you've got 5 minutes left to do this. Knowing that I want to undo a rate of change, I'm taking the antiderivative of the left side with respect to time, and I'm going to take the antiderivative of the right side with respect to time. On the left side, the dt's are going to cancel, and this is just going to leave me with the antiderivative of 1 with respect to p. And the antiderivative of 1 with respect to p is just p. On the right side, I can bring out the 30,000, and then I just have the antiderivative of 1 over t with respect to t. And this is going to be 30,000 times. What is the antiderivative of 1 over t? This is one of those rules you have to memorize.
The in
ln,
oh,
natural
sorry.
logarithm, yeah. Yeah, the natural log of absolute value t plus some constant. So this is almost our answer. I still need to figure out what is my value of c. So let's figure that out really quick. What is my value of c? Well, I do know that whenever the year was year 2020, that means my t variable would have been 20. And when the year was 2020, my population was 140,000. These are given to me in my problem statement. So let me plug in t is equal to 20 and p is equal to 140,000 into this formula that I got here. So I would write 140,000 is equal to 30,000 times natural log of 20 plus c. Well, so I'm trying to solve for this c. So on both sides of the equation, I'll divide by 30,000. And so 140 divided by 30 would be 14/3. And then my right side of my equation would be natural log 20. Oops. Hold on. That's probably not the right step to do. Because I'm trying to solve for c, right?
Could you just subtract? Oh, no.
Yes. I want to subtract. Exactly. So I do 140,000 minus 30,000 times natural log 20, and that's what gives me c. Yeah. Sorry, that was my bad. You guys are right. You guys are right. So if you had a calculator, you could take natural log of 20 and take natural log of 20, multiply times 30,000. Sometimes this takes a long time to load, but maybe we can do this in 2 minutes. Natural log of 20 times 30,000. And then I want to take 140,000 and subtract 30,000 times the natural log of 20. So c is going to have the value 50,128. So this tells me that c must have the value 50,128. So this is one of those word problems that I promised we would have, where the value of c is not 0. So again, bringing this back and plugging in that c value, the formula that gives me my population as a function of time is going to be 30,000 times natural log of t plus 50,128. And so that's answering the first question, is find that function that gives the projected population at year t. Well, there we go. That's a formula that gives the projected population at year t. And then for the next question where it says find and interpret capital F evaluated at 35, that's just telling you whenever the year is 2035, what would the population be? And you can use this formula that we just found to find that population at year 2035. Except I think I erased part of it. That's 50,128. Okay, so this is what I mean by when I say on an exam, I'm not going to like take off points if you forget to write plus c. But there will be questions like this one where if you forgot to write plus c here, you would have gotten the wrong formula for population. And all of your population estimates would be 50,000 less than they should have been, right? Because c wasn't 0 in this case. Any questions for Elga? All right. Good. Well, see if y'all can practice a few of these before next class. And next class we're going to be doing antiderivatives again, but we're going to learn what's called the integration by substitution method. And integration by substitution is kind of like the derivative chain rule, but not exactly. It's a little bit more complicated. That's what you have to look forward to.